Okay, so now I'm on this line right here about the expected second derivative with a negative sign is thus this equation here. Just as a reminder, we are reading through Nelder and Wedderburn, and we are on section 2.1. The link to this paper and the complete playlist that I'm making on this paper are provided in the description of this video. Okay, so what is this expected second derivative with negative sign? This is basically an element of the Fisher information matrix. Okay, element because you see I and J there. So you can see if we plug in 1, 1, 1, 2, 2, 1, etc., then we would have a matrix. Okay, then it follows directly from equation 8, which is right here. So I wrote equation 8 on my blackboard. There was a typo on the paper here. You see Z. It should have been an L. So I just marked that in blue on the blackboard. We discussed that previously. Just a small typo. Not a big deal. But something you need to keep in mind as you're reading through this and you want to show this, you want to prove this for yourself. Okay? So negative expected value of the second derivative of the likelihood with regards to your parameters. Again, Fisher information, an element of the Fisher information matrix. So go ahead and just plug this in, right? We have up top there, okay, we have what this is equal to this stuff right here. So go ahead and just plug that in. Let's see what we have. Okay. Now, x is not a random. It's not a random variable. It's like a constant, or it is a constant. So just a reminder, if we go back to our paper and we go up to the definition of where x was being defined, let's see right here. X are independent variates with values or are supposed to be known. So because of that, they are not random. Or at least in this model that Nelder and Wedderburn are developing, these are not random variables. These are known values. Beta is a parameter. Beta is also not a random variable. So because beta is not a random variable, y is not a random variable. Okay? Just while we're up here talking about what's random and what's not, v is the variance of the random variable times alpha of phi. So again, variance is not a random value, so not a random variable. Mu is the expected value of z. Okay, when you take the expected value twice, you're just taking the expected value of a constant. So mu, again, not a random variable. So what's our random variable? We're taking the expected value of likelihood. There's something's random, right? Well, the random variable is z. Z, remember z comes from this exponential family of distributions. So z is our random variable. Okay, so when we're doing this expected value, you got to keep that in mind. All right, so this x is like a constant. It can be pulled out of the expected value. Just like that. Okay, so we'll just put it at the end. All right, so now I have the second derivative of the likelihood with respect to y, which is basically what you see right here. So now it's time to plug in all this jazz for the second derivative of the log likelihood. So let's just be really careful with our parentheses as we do that. So I have equals negative expected value alpha of phi d mu dy squared divided by v plus z minus mu d alpha, or second derivative of theta with respect to y. Okay, close the parentheses for the expected value, and then I have that xi, xj chilling out back. All right, so now, remember my only random variable is z. So let's go ahead and just do some distributing to kind of make things a little easier. First thing I want to go ahead and distribute is this alpha of phi. So I'll multiply it by both pieces of the sum. Okay, and I'll get equals, oops, turn to green. undo that, equals negative the expected value of alpha of phi. Okay, I have this negative sign. I'm just going to put it out front. D mu dy squared divided by v. Okay, plus alpha of phi. I'm going to move this out front of the product. Okay, z minus mu. Okay, all right, so I've successfully distributed, close up those parentheses, xi, xj, still hanging out in the back. Okay, so now I want to go ahead and take this negative expected value and bring it in, because the expected value of a sum is the same thing as the sum of the expected values. Now this piece right here is just a constant. There's no random variable in it, so the expected value of it will just be itself. Okay, and then I see those negative and negative will cancel each other, so I'll end up with alpha of phi d mu dy squared divided by v minus, okay, because I saw that negative, okay, the expected value of all this jazz here. Okay. Oops, I closed those parentheses a little too soon. Z minus mu. Okay. Xi, xj. All right, so this is just a constant, so it can come out of the expected value. Okay, so I have alpha of phi. All right, the expected value of z minus mu. Okay. Make sure that I'm being careful here. I should be enclosing all this in parentheses. All of this is getting multiplied by xi, xj. Okay. Just like how here it was all being multiplied by xi, xj. Okay. Just make sure you've got your parentheses straight. All right. So now I have here alpha phi, so I'm just copying, leaving this piece alone, basically. Okay. Alpha phi, expected value, I can take of each piece. The expected value of mu, again, mu is just a constant, so that would just be mu. Okay. All right, expected value of z, by definition, that is mu. Okay, that is what mu is. So I have mu minus mu, which is just 0, right? So because this is being multiplied by 0, basically everything here is going to go to 0. All right. So then I'm left with just copying down this first piece here. All right, so this piece times xi, xj, right? And if I go back to my paper, okay, scroll back down to equation 8. All right, we see that's exactly what they have written here. All right, so we successfully have shown that the an element of the Fisher's information matrix equals what they've written there. Okay.